Welcome to March 15th, the Ides of March. And remember where that's from? Close. Different. I'm sorry? Close. Another one. Julius Caesar. Yeah, he was killed on the Ides of March. Okay. So today we're going to be in the middle of chapter 28. But just a reminder that we're going to have our second midterm. What was it? March 27th, which is a Monday. And then I also posted a discussion assignment for you guys to post what you want to review. So March, this is the midterm 2. And then we're going to do a review on it the Thursday before. When was that? What day is that? That's the 23rd. Right, March 23rd, the Thursday before the midterm. We're going to do a review where, as usual, I posted up a little, well, nothing is usual this semester actually. Last time we tried to do this, right, you had to email the questions to me. But on Canvas now, there should be a discussion post for you to post the top question from each chapter. So it's going to be 4 chapters, right? 28, 27, 26, and 25, right? And so make sure you do that as soon as you can. That way I can actually think about which problem to go over. So what I do is I kind of pick the problems that you guys like to see, right? Most of you guys think, oh, this is a concept that's not, getting across. And I want to make sure that it's something that's going to be likely on the midterm. So if something is, I know for sure it's not going to be on the midterm, I'm not going to review it for you guys, right? Because there's the point of the review is to get ready for the midterm, not to drone on about more interesting to me, but maybe less interesting to you physics stuff. Yeah, Chad?
Can you post more like how you did for the midterm review, like the types of questions to kind of go over? You post like kind of like go over these types of questions.
Oh, like posting like a list of problems? Yeah, I can do that. Yeah, definitely.
Yeah, that would be really
Because so I would just kind of just go to the back of the each of the chapters and just look for certain problems.
yeah.
And usually I look for the 2-bar problems. I think even on the e-text there should be like a, so on each problem, like let's say for example chapter 28, problem 50. Usually there's like 2 little bars on it. That means this is like a medium difficulty problem. Okay. Usually I look for those for the midterm. Okay. All right. But I can also post a few that I think the concepts are relevant for what you should expect on the midterm. Okay. All right. Any other questions about the midterm? All right. Let's get back to our little circuit stuff. Okay. So last time we talked about this idea of what's known as the internal resistance, right? Where the reason we need this internal resistance is that if you try to draw infinite current out of a battery or any power source, even if you try to draw infinite current out of the outlets here, right? What's going to happen is that it's not going to provide the same amount of potential slash also known as voltage for you, right? It's not going to stay 120 volts if you connect, don't do this, right? You get a paper clip and just connect the two of the side prongs together, right? It's not going to give you 120 volts for long because this is actually known as a short circuit. You're trying to draw too much current out of your your voltage source than you need it. And we saw that, well, if, right, the internal resistance is pretty small, right? In this case, we have a 5 ohm internal resistance. And let's say we put a resistor out here, also known as a load. Basically, it's just something you're driving in order to, could be a light bulb, it could be, a computer, it could be whatever you want, a microwave, right? It has a resistance of 250 ohm. What happens is that you will get a slight drop in the current, right? Because without this internal resistance, you will get exactly I without internal resistance, right? Oh, that's actually a lowercase r, right? You will get 20 milliamp exactly. So you get a little bit less current because of this internal resistance. Is that right? So Dr. Two, what's the big deal about this? Like, why do we worry about this internal resistance thing? Okay. But let's say you have the same battery, right? Now, instead of a 250 ohm load, let's say you have a 5 ohm load, right? You have like a motor or something that has a very low resistance to it. Okay, a lot of current goes through it, draws a lot of current, right? Let's say your starter motor on your car. Okay, and let's see what happens now if we reduce the load to only 5 ohms. Okay, so over here, what we can do is we follow the same Kirchhoff's loop law, right? And we derive the current. It follows the same equation. Okay, right? So the EMF, little r plus big R, but instead of big R being 250, now little r is actually only 5. Sorry, little r and big R are both 5. And the voltage was 5 volts. Okay, little r is 5 ohm. Big R is also 5 ohm. So I basically replaced this resistor with a 5 ohm instead, a much smaller resistor. Okay, so you get 5 volt over 10 ohm, and lo and behold, let me do that right. V equals IR. The amount of current you get out of it is 0.5 amp. Okay. Okay. So this is with internal resistance. Okay. Let's do the same calculations without the internal resistance, basically just ignoring the little r, right? Without the internal resistance, right, we don't have the little r, so it's just 5 volts over 5 ohm. And even I can do that division. That's 1 amp, right? So basically, the internal resistance without internal resistance, the internal resistance basically dropped the amount of current that that particular battery can provide by half. Okay, so it makes a bigger deal if your internal source resistance and your load is similar to each other. Okay, so that's sort of the idea of why we have to account for this. Okay, and as I mentioned, if you were to flex a couple of paper clips into the wall jack, what you can do is actually create this situation called a short circuit. So a short circuit means that you have a battery source, right? Whatever that is, a plug, a battery, your laptop charger. Well, what you did is you basically connected the positive end of your battery directly to the negative end of your battery. And this is where you're going to have sometimes a little spark. Sometimes the wire will get really hot. This is known as a short circuit, where if not for the resistance, the internal resistance, you would actually get infinite current, right? If you didn't have this model here, right, this is without internal resistance, okay? If you didn't have this model here, if you actually follow Kirchhoff's loop law, right, the battery is actually like this. Let's just draw it, the book draws it. If you make this connection here, right, if I follow Kirchhoff's loop law, right, that means, well, if I start off here and I gain EMF amount of voltage, right, and I came back to exactly the same place, right, you actually, it's saying that your EMF is actually 0. So you run into sort of a math dilemma there, okay? And even though you know, oh, maybe this is 9 volts or something like that, right? You're saying, so you're making mathematical statements that are not true just because you did not model with internal resistance, right? Oops, it's upside down. 2, 3, 4, right? There's supposed to be a little tiny resistance coming out of this battery, right? In this case, when you apply Kirchhoff's loop law, right, you will get E equals minus the current coming out of the battery times R, that's equal to 0. And that's going to actually allow you to solve it, right? Because this is nonsense, right? Because you can't have 9 equal to 0, right? So some examples in this textbook, right? And I suggest you go over that. And as I stated, okay, most of the time, the internal resistance is going to be much bigger to the external resistance, right, So it doesn't affect the circuit that much, but you should account for that if they are similar to each other. Okay. So there'll be certain problems that will say this battery has a certain internal resistance, and there's certain problems that just say, oh, this is a battery, and it doesn't tell you what the internal resistance is. In those problems, you can just say assume it's 0. Okay. Right. It's just different sections of the textbook will focus on different parts. Okay. All right. So the next section, as we kind of alluded to yesterday, is on parallel resistors, right? So just like capacitors, right? When we did capacitors, there was 2 different ways to arrange a capacitor or multiple capacitors together. This is known as series, right? Not the stuff on your phone, but series as in one after the other. Okay. And then there's the parallel configuration, right? Where the 2 capacitors are actually, it doesn't have to be next to each other, but then, the way you figure out whether something is series or in parallel is that just pretend you're a little positive electron marching along this. Do you have to go one after the other? If you have to go one after the other, that means it's series. If you can split up, let's say over here, and you can split into 2 different paths, that's when things are in parallel. One analogy I like to do is that, if you're in line at the supermarket, right? So let's say there are 4 people in line in the supermarket, right? The checkout person take care of one of you at a time, right? That's doing the job in series, right? But if there are 4 of you in line, but then there's 4 different checkout counters, right? 4 of you can actually go to its own checkout counter, so all of that checkout can be done in parallel. Okay, hopefully that analogy is okay. Same thing with the resistors. Okay, what happened is that we can combine, like, well, I'm going to do an example with 2 resistors, but these equation generalized to 3, 4, 5, 6, 10, 50 resistors if you want. So if we have resistors in parallel to each other, right? Let's say draw it this way. Okay, and remember the resistors is these little jagged lines, right? Is there a way for me to figure out, let's say this is R1, this is R2, some different resistance. Can I make this into some sort of equivalent, right, where I combine those 2 resistance together as, I treat those 2 resistor as if it's just one, okay? And remember the series version, okay, R1, R2, right? The equivalent in this case is just R1 plus R2, okay? Hopefully you guys can guess what the parallel version is going to be, right? It's going to be the more complicated formula, okay? But I'm going to show you how we can actually figure that out, okay? Let's say I connect this to a battery, okay? Right? In this case, we're not worried about the internal resistance because we're moving on to a slightly different concept, right? This has some EMF E, right? Squiggly E. How can I make this, right, basically the same circuit as this, okay? We want to make this the same thing, right? Behave the same way, okay? So what we're going to do is going to go on the left-hand side, and I show you just the answer on the bottom here, right? I'm going to apply Kirchhoff's loop law as usual, right? I'm going to start off at this point here, right? When I start here, I see a battery, right? I'm going to declare that the current goes this way. I see a battery, right? The next thing I see, right, when I get here, right, is going to be 2 different resistors, okay? Right? The main concept here is that, right, at this point here, right, you are at EMF, amount of potential, right, all along this wire. Remember, we're modeling these wires as if they have no resistance, right? All along this wire, we are still at EMF, amount of potential. Let's say the EMF is 9 volts, right? There's 9 volt here, 9 volt, 9, 9, 9, 9, 9, 9, 9, 9, 9, 9, 9, 9, 9, all the way up to here, right? In fact, when the wires split, the voltage stays the same on both wires, right? Because we're just traveling on that wire, okay? The current has to be split, right? I1 equals to I2 plus I3 but the voltage stays the same, okay? Because it's all on the same potential, okay? The analogy I like to show, right, is that let's say you're doing a little hike on the mountain, right? And then you go up to this path, but then there's two different, direction you can go on the path, right? The elevation you are at, even though you're on two different paths, you are still at the same elevation, okay? Okay? Therefore, you have the same amount of gravitation potential energy, and therefore at the same potential, okay? So over here, you are still at 9 volt. Over here, you're still at 9 volt. When you go over this resistor, right, you're going to lose the amount of current, which could be different between the two sides, times the resistance of that particular one, right? So what I'm going to do is I'm going to pick this as kind of path number 1, this as path number 2, right? So path number 1 is telling me that, well, when I go over this resistor, right, I'm going to lose I1, let's just say, I1, and this will be I2. I1 amount of resistance over R1, okay? And now, right, we're on the other side, right? The thing is, well, we started at 0 here, right? If we trace it all the way back, right, on the other side of the resistor is also 0, right? So we actually reach 0 once we get to the other side of the resistor, okay? Path number 2 is very similar, right? But now we're dealing with I2, okay? Right. Okay. So on the equivalent circuit is a pretty simple one where we just have a regular current, right? And this is just going to be EMF minus I times R equivalent, okay? One of the things is that at this split point, right, one of Kirchhoff's law is that the amount of current going into a junction has to be the same amount as going out. So therefore, right, this I here is the same I as here, right? I is going to be equal to 1 plus 2. Does that make sense? Right? We have I amount of current flowing in here, and we have I1 and I2 amount of current flowing out. So we have this little equation here. So what I'm going to do, forgot the 0 here, right, is solve all three of these equations for all their i's, and then just try to compare them, okay? So solving this equation for I, okay, this is going to be EMF over R equivalent, okay? That's what this goes to. Solving this equation for I is going to be very similar, right? It's going to be EMF over R1. Solving this equation for I is going to be EMF over R2. Okay? You can do that yourself at home if you don't trust me on that. Cool thing is that, well, look at all the E's, right? They all cancel out, right? On both sides, right? The same factor on both sides. Therefore, this is telling you that 1 over R equivalent is the same thing as 1 over R1, 1 over R2, or in other words, R equivalent is 1 over R1, 1 over R2, with a big -1 power on top, right? So that's the formula to figure out what the equivalent resistance is if you have resistors in parallel to each other. Okay. One thing to note is that since we're going to see that if you plug in numbers to these things, okay, parallel resistors will tend to reduce the resistance. Let's say you have a 10 ohm, 20 ohm, 30 ohm, right? The answer you're going to get is going to be less than 10 ohm. It's going to be less than the smallest one you got, okay? Right? Similarly, if you have resistors in series, right, let's say 10, 20, 30 ohm, right, since you're adding these number up, it's going to be bigger than the biggest one, right? So whenever you're doing calculations, right, and you found out a parallel resistor, and you say, let's say that your resistor one is 10, the other one is 20, and you found out the answer is 30, you probably did something wrong, right? It's always going to be less if it's parallel, right, but more if it's in series, okay? The way you want to picture this is going back to the cash register at the supermarket thing, right? If you have 4 people in line in series, right, it's going to take longer for you to check out, so there's more resistance, right? But if you have 4 checkout counter, each person is able to use his own counter, right? It's faster to get through there, right? So there's less resistance, okay, for you to get to, you know, your groceries, right? As I stated yesterday, don't have to memorize all 4 equations, okay? I will provide these to you, but I'm not going to say, the stuff, right? It's just going to be the stuff on the left, okay? But, okay, you have to know, okay, at least one of them, and you can actually logically figure out the other 3, right? So if I know that, series resistor follows this formula, I know that the parallel one will be the opposite of it, the harder one, right? And then capacitors are just flip from resistors. They behave opposite like the resistors, okay? All right. All right, so let's do a problem where we now have to calculate actual values from a circuit. Okay, let's do this little circuit here where it doesn't actually look like there's something parallel or series, right? Because it just looks like a bunch of resistors in arranged in like a square. Okay, so how is this a equivalent resistance problem? What I'm going to do is I'm going to pull out this magic where I'm just going to kind of move the resistors along the wire until it kind of makes it look like something parallel or series to each other. Okay, so I'm going to start off with the battery as usual. Okay. All right. The first thing I see after the battery is R1. Okay, so I'm going to draw R1. Okay. Okay. Next thing I see after the R1 is this junction point, right? So a junction point is a split in the current. Instead of drawing it like this, I'm going to draw it like this. Right? That's the same split, right? You're just splitting the path. Okay? If I follow this path or the upper path here, right, I'm going to run into R3 first. So I actually run into another resistor, R3. Right? Before I move on, what I'm going to do is I'm going to follow this path until R2 and see that, on the other path, instead of running to R3, I'm going to run into R2. Right? Now, if I follow both these paths, they re-merge back together, right, at point C here. So therefore, I can draw it like this. And now, right, it looks like we have a parallel resistor situation. Okay? Right? So after point C, what I see is R4, right? Therefore, I'm going to draw R4. Right? So this is, more compact, but this is easier to understand, right? And then so after R4, we have to go back to the battery, so I'm going to take this whole wire and just loop it all the way back. Right? Okay. So what we need to do is to basically make this look like just a single battery with one resistor on it, right? The R equivalent. So what is this R equivalent value? Okay. Why don't we have you guys chime in? So what should I do first? Which resistor should I try to combine together first, step by step, before we do anything else? Should I try to combine R1 with R2 together first? Yeah, because the reason I don't want to do that is because this is kind of in series, but then there's this parallel stuff next to it, right? So that's going to mess up my calculation, because I can only do either series in the equation or only parallel in the equation. I cannot mix the two up. So what I'm going to do is I'm going to combine these two resistors first because they are only series. Sorry, I said the wrong thing. They are only parallel, right? So I'm going to do, the first thing I'm going to do is to basically make this equivalent look like this first. Okay? And the notation I usually use is just R23. That means I'm combining resistance of 2 and resistance of 3, right? I'm going to make the circuit look like this first. Okay? If I'm combining 2 parallel resistors together, right, R23, right, follow this equation, 1 over R2 plus 1 over R3, all to the reciprocal, right? And R2 is 10, R3 is 20. Okay, so 1 over 10, 1 over 20, all reciprocal. Okay, so if you add this together, you get 3/20th. Yeah, so if you add this together, you get 20 over 3. Hopefully that's right. Yeah, so this is actually 2. Yeah, okay. So this is this equivalent here, right? Now the problem is much nicer. Right now all the resistors are only in series. I know how to add that, right? I know how to add series. I know how to add parallel. I don't know how to add the mixture of the two, right? So R equivalent here is actually R1 plus R23 combined together plus R4, okay? And R1 is 10, and I will write in the units this time even. And R2 is 20 over 3, that's in ohms, okay? And then R4 is 20 also, okay? So if you add all these numbers together, make sure I need my phone. What's 20 over 3? It's like 6.666 or something like that. Where's my phone go? Did I just not bring it? Yeah, I don't think I bring it. Okay, I don't have my calculator. So what's 20 over 3? Anyone? 6.67. Okay. Right, 10 plus 20. So this is going to be 36, and we're doing 2 sig figs, right? So that's going to be 37 ohm, okay? That's the R equivalent at the end. Make sense? All right. So when you run into these circuits, redraw it so it looks like, it forces this thing to either look parallel or series to each other first. Then you have to deal with one of them at a time. You cannot deal with both of them at the same time, okay? All right. So in the textbook, there's a much nicer example, so hopefully, so if you guys were to try to find the equivalent circuit of this, equivalent resistance of this, which two resistors do you think you want to deal with first? 90/45. Right, these guys, right? You want to combine these guys together to make it one resistor, right? Now that you have one resistor here, right, you can add these in series to each other, right? And then that's big, make one big resistor here, right? And now you can add these parallel resistors together, okay? You have to do it one step at a time, okay? Either only do parallel or either do series. Don't try to do both at the same time. All right. So next we have a little interesting light bulb puzzles, okay? Where let's say we have some battery and we connected it to 3 different light bulbs, okay? And light bulbs kind of basically behaves like resistors at, moderate amount of current, okay? So, and the brightness of the light bulb is based on how much power is being dissipated by that light bulb slash resistor, right? Okay. Remember from the couple of sections ago, right? We calculated the power that's coming out of the resistor is either the current times the voltage drop across that resistor, or I squared times R, or V squared over R, right? So what we're trying to figure out is that, let's say we connected these 3 identical light bulbs, so all of them will have the same resistance, just some resistance R, right? Well, first of all, in this case, which light bulb will be lit up in the first place? A, B, or C? Which one has current going through it if the switch is open still? A and B, right? C doesn't have current because this got disrupted, right? Even if you try to follow this path, there's no way for the current to go back, right? Right? In order for you to have a current, it has to be a complete path, okay? So this light bulb here will be basically the same brightness as this one because you have the same current, you know, let's say call it I, going through both light bulbs, right? But if you close this switch, right, let's say we make this connection here, right? Instead of just a single current, now we have 3 different currents, right? I'm going to call this maybe IA. I'm going to call this IC. I'm going to call this IB, right? Since the resistance are the same between them, right, the amount of power that's coming out of the light bulb is just proportional to the current square, right? So which of these light bulb has more current, that has the most current going through it? What do you guys think? A, right? Because whatever B and C is the sum of those two combined together will give you A. Okay, and let's see. And I think B and C will be the same amount of current because you can actually redraw this circuit like this, right? This is A, and this is kind of B, and this is C, right? B and C are basically parallel to each other, okay? So these two are actually the same, right? If the resistance on the light bulbs are the same, okay? All right, so that's sort of an interesting thing where by closing the switch over here, it made A brighter, right? And then and B and C are both lit up, okay? Let's do another one, okay? The stop to think wants you to rank in order, but since we're in person, we just have to kind of raise our hand. Let's look at this circuit here. Now there's 4 light bulbs that has the same resistance, okay? Which light bulb is going to be the brightest? What do you guys think? This has some resistance R, right? Same resistance. How many of you guys think it's A? All right, most of you guys, good. And so I won't go through the other one, so it is A because just as the previous example, right? Right, this is the amount of current going through, right? And this current gets split between this path, let's call it I2, and this path, right? So the sum of those two current has to be bigger than the constituents. So therefore, it has to be the biggest one. Now the harder part, right? Which one's the second brightest light bulb? Is it B or is it C or D? This one's more complicated. Okay, how many think? Well, we know it's not A because we picked A for the brightest already. How many of you guys think it's B? Okay, fewer people. Good. Okay, how many of you guys think it's C? What about D? Okay, so we got like about 5, and then maybe 2 and 2 here. Okay, so let me just work through which one it is, which one I think. Well, let's just work through the mathematics and see what happens. Okay, so remember that the amount of power coming out of a light bulb is basically the current square times the resistance of that, right? Okay, so by comparing, you know, so which one is bigger, I2 or I3? Which one is bigger, right? Right? We don't know which one is bigger yet. Okay? Because if I2 is bigger, right, then C and D will be brighter. If I3 is bigger, then light bulb B will be bigger, right? Okay? Since light bulb B has 1 times the resistance of a light bulb going through on it, right? But then I2 has 2 different light bulbs going through it, right? Which one will encounter more resistance? I2, right? It's basically like kind of going through two different lines, and let's say you have to check out twice in a supermarket, or you know the current's going through 2 cobblestones and with reeds kind of resistance, right? So there's more resistance here, right? Right. Therefore, the more resistance, the smaller the amount of current, right? It'll slow down the current. So therefore, we can actually figure out that, well, I2 is actually going to be less than, right, less than I3. If we know that I3 has to be bigger, then therefore, right, light bulb B has to be the brighter one. Does that make sense? Okay. Right. So you can figure all this out without plugging in numbers, okay? All right. Any questions about, these slightly more complicated circuit before I go on to even more complicated ones? Yeah, Alan?
Scroll back up to the previous graph.
Mm-hmm.
Resistors are connected in parallel. Their combined resistance is less than.
Right. Right. One thing you can do is you can model this, right? You can well, you're gonna play around these circuits quite a bit, right? Because you have one resistor here. You can draw a equivalent here, combining B and C together, right? R of B and C together, right? And this will be smaller than either resistance of B or resistance of C, right? So this will give you more current combined together than they are separate, but that makes sense, hopefully, right? You have two different rivers, right? You're going to have more current, okay?
So does that mean that when the switch is closed, A is actually brighter than when it was open?
Right, exactly, yeah. Bright, A actually turns brighter. And actually, I think we have a demo for that, actually. And I'll show you guys that maybe tomorrow, okay? All right, yeah, chat?
For that one, the dimness bulb would be D then?
I think both C and D are the same dimness. That's why I didn't ask that question. Because they both have the same current. If you have the same current, the same resistance, the power dissipated should be the same, right? Okay. All right. Now, let's collect all this stuff together, right? And try to analyze resistor circuit. And this is going to be something that, one of the combined things in this chapter that's going to be important for us to figure out how to do, okay? So let's just go through the analysis of maybe like this circuit where, right, there's multiple resistors and there's multiple batteries also, right? Okay. And this is going to be a two-loop circuit because what's happening is that, let's say you start off, you kind of have like two different paths that the current can go in, right? And this is typically where one of the hardest thing for circuit analysis for students to pick up on. And the idea is that you really just want to follow Kirchhoff's two laws, right? Which is that the sum of the change in voltage around a loop is 0, and then the sum of the current going into a junction and the sum of the current going out of a junction is going to be the same. Okay. The other important thing is actually also Ohm's law. The change in voltage across a resistor is I times R, and this is always a drop, okay? Okay? So let's see what happens. Okay? And so in this little example, they want you to find the current and the potential difference across this 100 ohm resistor. Okay? We're going to do it for everything, but the answer is actually focused on that, okay? So to start, right, I need to somehow, so this is sort of like the setup. We draw this diagram. Somehow I have to translate this diagram into something with math and equations in it so I can actually deal with the moving, do algebra with it, right? So the first thing I'm going to do, okay, I'm going to pick the biggest battery, okay? I'm going to say that, well, I'm going to assume that the current follow the direction of that battery, okay? It's not always going to be true, but like 80%, 89% of the time it's going to be true, okay? The biggest battery wins, okay? Since we're going to have multiple currents, I'm just going to call that I1, okay? Just so we have I1, 2, and 3, okay? If we keep going along here, right, this current actually gets split up into two, right? So I'm going to call the one that's going down here I2, and then there's going to be one going across here I3. Okay, right? Both quantifying it, meaning labeling I1, 2, and 3 are important, but the arrow is also going to be important, okay? Because that tells us if we're going the right way on the battery or the opposite way on the battery, right? So what I'm going to do is I'm going to go over here. I'm going to pick a particular loop, okay? A particular loop, meaning you're just going to pick a particular, those of you who goes hiking, you can pick a particular loop, right? You just taking a path so you end up at the same point as what you started with, okay? And a lot of times students are just confused, like, I don't know which loop to pick. Doesn't matter, just pick one of them, okay? So let's say I'm gonna start here. I'm gonna walk around. I'm gonna go through the other battery and come back to the same point. That's a loop, okay? Okay, that's gonna be called loop number 1, okay? I can also maybe start off at the same point, right? Go on my little hike and go the long way around and come back this way, right? That's loop number 3, okay? There's actually, loop number 2, okay? There's actually a third loop, and typically you don't need the third one, right? Remember, for these loops, you can pick at any point on the circuit, and you can walk on the path, and as long as you come back to the same place, you are in a loop, right? So let's say if I start off at this point instead, this purple point, and I march around here, right, I can come back to the same point. That's loop number 3, okay? Okay. So each of these loop, if I apply Kirchhoff's loop law to it, right, I'm going to get one equation. So right away I have 3 equations out of this, okay? Right? And then this fourth one, this fourth equation, actually comes from the current going in equals current going out. This will actually give you the fourth equation, okay? So we'll see if we need all 4, but let's just start with loop number 1. Let's just do that in green. Loop number 1, if I start off at this point, if I go along this loop, right, the first thing I'll see is a battery, okay? So I'm going to call that EMF1, just so I can have variables instead. EMF1. Let's erase this. Let's call this R1. Okay. As I follow this loop, the next thing I see is actually a resistor, right? I'm going to lose some voltage across that resistor that's equal to R1 times I1, right? Because that's the current on that loop. Okay. Then I keep walking on here, and I see this junction, right? But I'm going to choose to go right because on that loop, I'm going right. Okay. And next thing I see is another resistor. Let's call that R2. Okay. I'm going to lose R2 times, instead of I1, right, on this particular part of the path, the current is I2, right, not I1 anymore. Okay. Now, next thing I see is a battery. I'm going the wrong way across the battery. So instead of gaining EMF, I'm going to lose EMF. So that's called that EMF2. I'm going to lose EMF2 amount of voltage. And now at this point, I'm going to turn right and end up at the same point. When I end up at the same point, I can say that's equal to 0. Okay. This is equation number 1. Okay. Before you write more equation, okay, before you do more math, okay, the thing we're interested in solving for are the currents, right? Because we know what EMF is, we know what R1 is, R2 is, we know these numbers, but we don't know I1 and I2, okay? If I have 2 variables with 1 equation, I don't have enough information, right? So what I need to do is find another loop, okay? What I'm going to do is I'm going to follow loop number 2. Let's do that in red. Right, loop number 2, I start off at the same place, right? It may look like it's the same equation, right? The first thing I run into is R1, right? But instead of turning right, I'm going to go straight, right? If I go straight, I actually run into resistor number 3, right? This is going to be R3 times I3, right? After this resistor, I actually can go back to the beginning without seeing um, without seeing the other battery. Okay, I'm gonna write the other equation, loop 3, but we're gonna find out that we actually don't need it, and we're gonna say, okay, why do we write that? But it's just good to practice writing these loops. Okay, so remember loop number 3 is the purple one, where we start off here, we go the correct way across battery number 2, right? But now we are going against the current through a resistor. Okay, right? If you follow the current through a resistor, you lose potential. But if you go against the current across a resistor, you actually gain potential. It's like swimming upstream. Okay? So instead of minus, you get plus I2 times R2 of potential. Okay? If you keep following this, okay, we're following this purple loop, right? Next thing we see is R3. Now in this case, right, we're actually going the correct direction. We're going downstream, okay? So you actually lose potential R3 times I3. Okay. The reason I said that I actually don't need this one is because if we go back here and count the number of variables, right? We don't know this, we don't know this. So we have 3 variables with 2 equations, okay? We need a third. It's actually more useful most of the time to actually use this as the third equation, which is the Kirchhoff's junction law, right? Where the current going in has to be the current going out, right? The current going in to this junction is I1. The current that's going out is I2 and I3. So therefore, we actually have a relationship between I1 and I2 and I3, okay? Because what you can do is that, well, since I have I3 here, right, I can actually get rid of that, okay, by doing a substitution. I solve this equation for I3. I3 is I1 minus I2, and I just substitute it back in here, okay? So the new equation 2, it's good to keep track of this, is R1 I1 R3 1 minus I2, okay? All of that equal to 0, okay? Okay. Since I'm trying to combine these 2 equations to solve things, right? Now we have 2 unknowns, right? 1, 2, same unknown, and 2 equations. 2 equations with 2 unknowns, then it's just, you know, algebra time, okay? So I'll show you guys the technique to solve these things, okay? What I like to do is actually line up all the i's, okay? And then do a subtraction between the 2 equations, okay? And we're going to see how that happens, okay? So I'm going to line up our equation number 1 here, okay? Minus R1, put the I here, minus R2, put the I here, okay? Minus EMF2. All that is equal to 0. What I'm going to do is I'm going to distribute this R3 to both terms, okay? So let's do that before we go on. 1 I1 minus R3 I1 plus, right, because there's no negative signs here, plus R3 I2 equal to 0. So now I can actually combine these 2 terms together. The EMF1 minus R1 plus R3 times I1. That's going to be R3 plus I2. Okay, right? I basically factor out this I1 out of both terms. Okay. Now I can rewrite this and pull this over here and basically line up the same stuff together, right? I have EMF1, right? The stuff in front of I1, I'm going to line up with I1. The stuff that lines up with I2, I'm going to line up with I2. Wait, did I write something wrong? Yeah, you guys didn't correct me. Right, I didn't copy this equation down correctly, so that's going to cause a big problem. So the problem with all this is that if you make a minor mistake, it's going to mess you all up. So unfortunately, that's the way of math, right? Plus R3I2. We don't have an EMF2, so we can just leave that blank, and this is going to be 0. Okay? Okay. To solve for one of these variables here, there's two different ways to do it. You can do a substitution where you solve for one, and then you do a substitution into the other equation. The other way to do this is to actually solve this way, known as a system of equation, where you basically add these two equations up together, but you add them up in a special way. Okay? So I want to get rid of one of these variables, and I think the one in the answer we actually want is actually I2, so we want to preserve I2 in the equation. Okay? What I'm going to do is I'm going to multiply the top equation by R1 plus R3. And then I'm going to multiply the bottom with R1. Big brackets. Why am I doing this? Okay, we'll see. Okay, if we bring this over before we add them, okay, this is going to be R1 plus R3 times EMF minus R1 times R1 plus R3 I1 plus R2. Maybe this is not the most efficient way, but it's systematic at least. I2 plus R1 plus R3 EMF2 go to 0. Right? Anything times 0 is still 0, so we're good with that. The second equation here, right, is negative I1 R1 F E1. And if I multiply this through, negative times a negative is positive, so we get R1 plus R3, all multiplied by I1. And then the next one is R1 R3 I2, and all of this is 0. Okay, and now hopefully you can see why I picked that particular stuff to multiply by. If I add these two equations together, these two terms subtract each other out to 0 exactly. Okay, right? These two terms actually also subtract each other out, so we have R3 epsilon 1 E1. This stuff here, right? We add them together, right? We're going to have minus R2 R1 plus R3 minus R1 times R3, all multiplied by I2, okay? And you have the rest here, R1 plus R3 E2 goes 0, okay? Then you solve this for I2, and I2 is going to be this long complicated thing, E. So let's do this in 2 steps because I can't do it in 1 step. Move everything to the right. Goes to R2, R1. There's just a lot of writing. 3, right, I2. And then you divide both sides by this. And then you have this complicated equation. R2, R1. Did I do that right? I just want to double check. Yeah, so this multiplies all of this. Sorry. Okay. And then if you plug in all those resistor values and EMF values, you will get the answer for I1. Whew. Okay. And so that's how you deal with these complicated